Hey guys, this video is being posted for MATH6620 or possibly any other class that I may decide to use it in. The purpose, or at least the focus in these upcoming videos are something we call correlation and regression. Correlation is just a method that we use to examine the relationship between variables, two quantitative variables, although we do get into a situation where we look at correlation across uh, a categorical variable, a dichotomous variable, and a quantitative variable. But this all leads into prediction. Or, I'm sorry, this all leads into regression. So taking these two as a pair, they're very important in education research because they allow us to investigate models which can be used for prediction. Now, I think it's safe to say that prediction is kind of fascinating to all of us. As I decided today, I don't know when you guys will be watching this video, maybe in the summer and when it's 90 degrees out, but the day that I'm putting this up, it's about, well, it looks like it's about 4 degrees. We have about 7 inches of snow on the ground. And, in the previous days, we've all kind of been glued to the weather forecasters as they try to predict the snowfall amount. And in this particular snowfall, they predicted 1 to 3 inches. We got 7. About a week ago, they predicted we'd get 4 to 6, and we got 1. So the whole weather prediction thing is something I think that fascinates all of us because, we're, hey, we're going to get out of class. Is school going to be canceled? All that kind of stuff. But prediction also could, make us extremely wealthy. If we were able to come up with a prediction model, whereas we could go to Las Vegas and predict, where the ball is going to land in roulette or what's going to be the next card in blackjack, we could become very wealthy. In fact, if we could even come up with a prediction model that could be used to determine what team in college basketball or college football is going to cover the spread, well, it would be called early retirement in my situation. But so again, prediction I think is something that kind of is fascinating to all of us, certainly as me. But more relative, or more relevant to education research, we might want to be able to create a model that can predict whether or not a student will pass their class or whether they will graduate from college. For example, I'm starting to teach a lot of undergraduate statistics classes online, and I'd like to know what demographics, situational, dispositional, academic data could be used to effectively predict whether a student will be successful in this level class. So anyway, what we're going to do, we're going to take this prediction, kind of prediction idea, and we're going to move it into the application of two quantitative variables. Now, guys, before we get started, SPSS is a statistical software package that is very, very, very commonly used, frequently used in ed research. And the data sets in SPSS have an ending of .sav, so an extension of .sav. And what I want to demonstrate to you right now is just how to get these data sets into R. So guys, first thing I'm going to do is I'm going to get out of this. So let me see how I do that. All right, so I want to minimize that. And what you'll see is I have a data set on my desktop called Exam Anxiety. Now what I'm going to do is I'm always going to rename that and just rename it as something, just one word, and that's just something I do. You don't have to do that, but something I do. Now, when I go into R, first thing I'd want to do is set my working directory, and then I want to get my data. Well, guys, to get a SPSS file into R, the first thing we have to do is we have to install the package foreign. And I think I've already done that on this computer, so all I have to do is just access the library. Now, obviously, if you haven't installed foreign prior to this video, watching this video, you would have to go install .packages, quote-unquote foreign, and just like we've done before. Now, the next thing I want to do is I want to get the data into R. So I'm going to go read.spss, and yeah, I called the I did call it yeah, anxiety, yeah. And then I have to data frame equal true to make this thing actually happen. So now if I attach my data, and I can see I have my data that I've imported in from the desktop. Now, sometimes, not always, but sometimes it'd be nice to have this kind of exported out of R and put it into a .csv where we can just really easily get it into R. And if we want to do that, it's just an easy command, just write .csv, and I want to write my data file data, so that's what I called it, and then I just decide what I want to name it on my desktop. So guys, now I'll go to my desktop, clever little feature here, and you'll see I have an extra data set, but it's in a .csv extension. Now you might say, well, why did we do that? We didn't need to do that because we already had it in our, guys, just a little extra stuff. Now, the first step, let me get back out of this. We're going to come back to R in just a second, but for now, I want to go back to the presenter. And what I want to concentrate on now is how do we examine the relationship between two quantitative variables? Well, the first thing we ask ourselves, do the variables covary? And covary just really expresses kind of an average amount of data variation around the mean. Now, when I think of covary, I can look at something embedded in covary and automatically I think variance. And guys, if you remember back from many moons ago, we find the variance of a data set by summing up the differences in the observations and the mean squared divided by the degrees of freedom, or n minus 1. So what that does, it takes each data point and subtracts it from the mean, so it examines the distance from the mean, squares it, and divides by the degrees of freedom, and of course sums all that stuff up. But what happens when we have two variables? Well, the covariance of two variables is just an extension of the variance of one variable. So what our focus changes to is not necessarily, again, in the variance, the difference between the observation and the mean, but we focus on if one variable changes from the mean in one direction, how does the other variable change from its mean, and what direction does it change in? So obviously if we have a situation where most of the data points are above the mean, corresponding with the other variable being the data points above the mean, then we have a direction, a positive direction, or covariance. Whereas if, like my x variable, the variables that are above the mean, the observations that are above the mean correspond to values below the mean for the y variable, then we have a negative covariance. So that's a lot maybe to wrap your mind around. I think it's going to be a lot clearer with an example. So let's just take some values here, some that I've already looked at. So the first data point would be 5.8. The next would be 4.9. The next 4.10. The next 6.13. And the final is 8.15. So we have a small data set, n equal 5. Guys have already gone ahead and calculated the mean. The mean for x was 5.4, and the mean for y was 11.0. My standard deviation, which I don't need now, but I will need later, is 1.67 and 2.92. So guys, what we can see here is we can see a pattern going on with our data. So we have 1, 2, 3, 4, 5 observations. And I'm going to just do a couple of the observations here. So for X, I have a mean of 5.4, which would be about right there. So X bar for X, and then the mean for my Y is about right here. So that's the X bar for the Y. So I can see that my first value is just a little bit below the mean. My first value for Y is also below the mean. 4 is about 1.4 units below the mean. And the Y, 9, is about 2 units below the mean. 4 and 10, 4 is 1 unit below the mean. 10 is actually just a little bit below the mean. So what you can see is this observation is below the mean, its corresponding values below the mean. This value is below the mean, that's below the mean, and we can go ahead and see that 6 is above the mean, 13 is above the mean, 8 is above the mean, and 15 is above the mean. So we know we're going to have a positive covariance because our X values that are below the mean correspond to Y values below their mean. So guys, the calculation for this turns out it's very, very, very simple. So we can look into the covariance for X and Y. And guys, it just turns out it's the sum of the deviations for X. Can't stand it when my paper's not straight. The deviate times it's what's the product of the deviations of X from their mean and Y from their mean. And guys, we divide by n minus 1. So the very first term, if we were to look at this, the very first term, the X is see negative 0.4, and the deviation of the Y was negative 3. And we could go ahead and, of course, divide all this by 4. And guys, we end up getting a covariance of 4.25. Now, this is a good measure of relationship. Again, a positive covariance tells us as one variable deviates from the mean, the other variable deviates from its mean in the same direction. A negative covariance just tells us as one variable deviates from the mean, the other variable deviates in the opposite direction. Now, covariance is fine. It's easy to find on on R. The command on R is just COV, X comma Y. But a major concern with covariance is the units or the scale. Now, if in the previous example, if X and Y, for example, were in miles, then our covariance would have been 4.25. However, if we convert these to a different measurements, for example, if we moved it to kilometers, then the covariance is not equal to 4.25. In fact, the covariance would be equal to 11. So guys, the covariance is not a standardized measurement, so it makes it impossible to compare. For example, if we were looking at the covariance between ACT and maybe a student's first-year GPA versus the covariance of SAT and first-year GPA, we would get different values for the covariance, although the relationship between the two may be very, very, very similar. just because ACTs have a lot less variation, 0 to 36, than do SATs. So, guys, we need a way to standardize covariances. So, guys, it turns out that a standardized covariance is precisely what you probably thought it would be. It's just our correlation coefficient. Guys, typically our correlation coefficient is given as a lowercase r. So guys, r is going to be the covariance for over x and y divided by the product of their standard deviations. So you can see that the covariance for x and y is just equal to 1 over the product of the standard deviations. So we know that the covariance is the sum of the x sub i's minus x bar, y sub I minus y bar over n minus 1. And this is over 1 times the product of the standard deviations. So guys, the Pearson correlation coefficient formula would be the sum of the x sub i's minus the x bars times the, in the denominator, n minus 1 times the product of the standard deviations. Now, using the previous data set, the one with n equal 5, not the one that we've imported, our R value would be, our covariance was 4.25, and our standard deviation for our x's was 1.67, and our standard deviation for the y's was 2.92. So, all right, so I'm sorry, I got a text and I got distracted. So the great thing about the correlation coefficient is it is a standardized measure, and correlation coefficient is always going to fall between -1 and +1. So as we get further to +1, we have a stronger positive correlation. As we get stronger toward or closer toward -1, we get a stronger negative correlation. So guys, we had a value of 0.87, which indicates a a strong positive relationship. Now guys, remember R is another way of examining effect size. So remember 0.1, 0.3, and 0.5 are the, I don't know why the dog is barking, but it seems like it always happens when I put up a video at home. So I actually had students previously.
I'm not sure.
Now Alexa's gone crazy. So things are getting freaky here, guys. So anyway, this is for the effect size. 0.1 is a small effect, 0.3 is a moderate effect, 0.5 is a large effect. Sorry, but my wife's cracking up back there. All right, so what happens? We want to generalize this because, that's what statisticians tend to want to do, right? We want to find values from our samples and generalize it to populations. So, much like we would do if we wanted to take a sample mean and generalize to a population mean, or if we wanted to take the difference in two means and generalize it to the difference in population means, we can do that. So, turns out that Z follows a normal distribution if the distribution from which it comes from is also normally distributed. The problem with this is R does not follow a normal distribution. But Fisher, probably one of the greatest statisticians ever, found that we can do a slight adjustment on R. So Z for our R's follow a normal distribution. I should have written this down. Could I forget? No, okay, I remember. If we follow this adjustment. Turns out that the standard error in this case is 1 over the square root of n minus 3. So guys, what we could do here is we could take our R value and generalize it to the population parameter rho. So again, this would be a value that we could get from our sample, and we could generalize it to the population value, the parameter of rho. So rho is like mu. Standard deviation could estimate the population. Standard deviation, not well, it's a biased estimator. Sigma, so the same thing that we have here. So inquiring minds would always want to know, is our correlation coefficient statistically significant? So what we would carry out there is a test of hypothesis. The assumption would be that the population correlation coefficient is equal to 0, indicating that there's no linear relationship. And of course, the alternative hypothesis would be that the correlation coefficient is not equal to 0. Now, it turns out that the test statistic that we use in this case is actually a t statistic. Now you might say, well, why did you even mention the z statistic earlier? And I really don't know now that I think about it. Maybe I just wanted to sound smart, or maybe I was distracted by Alexa and the dog barking. But nevertheless, if we want to test this, the test statistic is going to be found by taking r times the square root of n minus 2 over square root of the quantity 1 minus r squared.
Using artificial intelligence, scientists are learning how to translate vocalizations and facial expressions of animals into something that humans can understand.
Alexa.
Now,
okay, I have no idea what's up with Alexa, but Alexa's lost its mom. Okay, so, oh goodness gracious. So this t follows the t distribution, degrees of freedom n minus 2. So I don't really know why Alexa thinks that I'm using artificial intelligence. So
sorry, I'm having trouble understanding right now. Please try a little later.
I hope you guys can hear that. Otherwise, you're going to think I'm losing my mind. All right. So this is really funny. So let's go back into R, and sorry, I'm having way too much fun with Alexa. Don't say that. No. All right, so let's create some x's. Let me go back to my data set. So we had what, 5, 4, 4, 6, and 8, and our y values were 8, 9, 10. Shoot. So 8, 9, 10, 13, 15. Now, if I want to create a data frame from this, it's not a bad idea to do this. So I could just, create, say, new data. And so you make that for my x and my y, and then I would attach new data. All right. So, guys, two types of correlation. We have what's called a bivariate correlation, which is either a Spearman, Pearson-Spearman-Rowe, or Kendall's-Tau. And then we have partial correlation, which examines the relationship while controlling for the effect of something else. Now, you might think of a partial correlation coefficient kind of like ANCOVA, where we kind of adjusted the variation from the effect of something else, another variable. But guys, in its most basic form, we could do the covariance between X and Y, and we can see that it was 4.25, just as we calculated earlier. Or if we want to do just a basic correlation coefficient, we can get 0.86, I'm sorry, 0.87, just using COR X comma Y. Now, if we want comma Y, we can, if we want another method, we can, for example, use Spearman, or we could also use Kendall. All right, so they give us different values, but guys, Spearman rho and Kendall tau, let me write those down. So the three of the bivariate correlation coefficients, we have Pearson, which I'm just going to say is the standard. We have Spearman, and we have Kendall's tau. Think that'll be a test question? I don't know. I think of these two as being a non-parametric. You know, if we had maybe survey data, which was on a Likert scale, 1 to 5 or 1 to 7, you know, we wouldn't expect the underlying probability distribution to be normally distributed, so we'd use Spearman's rho or Kendall's tau. Now, if we want to conduct a test of hypothesis and get a p-value, then we would use a different command, and what I would use here would be core test between x comma y, and you can see what we'll get there is we get a test statistic, we get a p-value. Our p-value is not less than 0.05, so we have statistical significance at the 0.10 level, but we do not have statistical significance at the industry standard of 0.05. And it gives you your 95% confidence interval, and of course it gives you your sample estimate from which we conducted our test of inference. So, again, you know, we're assuming that data are normal, quantitative, measured on an interval scale. So, guys, let's go back to the original data set, which I called data, so I want to attach it. And I want to go names of data. And you can see that what we have here is we have a code, revise, exam, and anxiety. Exam, anxiety, and gender. So exam and anxiety are two quantitative variables that we may be interested in looking at the relationship. So the covariance, exam anxiety, is negative 1.96. So that tells me that as the exam score deviates from its mean, the anxiety score deviates in a different direction from its mean. So higher exam scores relate to lower anxiety scores and vice versa. Now, if I want to standardize this, I perform a correlation, COR. So I get a negative 0.44. So this is a standardized covariance. So I've standardized the measure. So what that means, again, standardized just means that we can compare the relationship across different types of study. Now, I would always probably be interested in looking at a t-test. So guys, here we have a relatively large test statistic, degrees of freedom 101, and our p-value is statistically significant at the 0.001 level. So we would reject the null and conclude that there is a linear relationship between anxiety and exam score. So kind of cool stuff. Now, another thing that we want to do is we may want to look at a correlation matrix. And the way we do that is we just do core data. So this is going to throw in code and revise and exam, anxiety, gender, the whole shoot and match, but it's going to give us an error. And the reason it's going to give us an error is gender and I believe code. I have to go all the way back up. Yeah, code. So just revise, exam, and anxiety are truly quantitative measurements. So if I wanted to create just a correlation matrix for the three quantitative variables, what I could do is, all right, let me get this right, revise, exam, and anxiety. So that should work, yeah. So this gives me a correlation, and correlation matrices are almost a standard reporting tool when conducting conducting regression techniques. So we can see that revise and anxiety have a moderately high negative correlation. Revise and exam have a kind of moderate positive relationship. Now, again, we talked about earlier, what happens if you do get into a non-parametric situation? Well, then you're going to use either Spearman's rho or Kendall's tau. And what would be the difference? And I don't know this to be true, but this is what I've learned, and I'm sticking with it. If we have a larger data set, I always report Spearman's rho. And if I have a non-parametric situation where I have a small data set, I report Kendall's tau. Now, final thing I want to cover in this video is another kind of correlation called biserial or point biserial. Now, unlike the previous, where both x and y are quantitative, for a biserial, as it may kind of indicate to you, or a point biserial, one variable is dichotomous. Now, on the heels of logistic regression, we know dichotomous means that we have a categorical variable with two possible outcomes. So true or false, gender, male or female, succeed or not succeed, live or die. If we were examining hospital data, is situations where we could have one variable is dichotomous. So one variable is dichotomous and the other is quantitative. So, guys, a decision on whether or not to use a biserial or point biserial is kind of really up to the nature of the dichotomy. Now, could I be more confusing? So all right, so it depends on the nature of the dichotomy. Well, guys, I'm writing, and I just kind of assumed you guys were seeing what I was writing, and you weren't. So that's what I was writing during that uncomfortable time of silence. So essentially, guys, what you can determine here is, did the dichotomization come from discrete variable or continuous variable? Now, something discrete is the classic form of a dichotomous variable, male or female, pregnant, not pregnant, left or right hand, dominant, true or false. Guys, in this situation, we would implement point-biserial methods. Now, sometimes in statistics, we take a continuous measure and we dichotomize it. And we do that a lot for pass-fail measures. For example, if we're looking at a percentage from 0 to 100 on an exam, you know, we often draw that magic line in the sand at 60, where these students fail and these students pass. Now, even though fail and pass is dichotomous, we have created this dichotomy by dichotomizing, splitting into two parts, a continuous variable. So when we get in a situation like that, we have a continuous measure that's been dichotomized. Another situation like that would be, you know, in my opinion, you know, whether a student graduates or not graduate from college. You know, if you think about to graduate from college, you go anywhere from like 126, from 0 to 126 hours. Anything above 126, you graduate. Anything below, you don't graduate. So if a student has 125 hours and they don't graduate, to me that's a lot of difference between just having 5 hours. So guys, put that on the radar, put it in your notebook. It is something that you encounter from time to time. Now, let's go over to, I don't know how I want to do this. I'll tell you what, let's go back to R and let me show you how to handle one of these. So let's dichotomize exam right now. It's a continuous, so if I take core exam over gender, you know, I'm not going to get a correlation, and the reason is Y must be numeric. So if I come back up, I can see that the gender is coded as males and females, but if I coded these as zeros and ones, I could get a correlation. So guys, what I'm going to do, I'm just going to do an if-else. So if gender, and I don't know why, but we have to use two equal signs there. Male, then we give our condition, and then we give our otherwise. Now I have, you know, a dichotomous, so I can use the simple if else like this. So in other words, that command tells me that if gender is equal to male, we're going to assign a 0. Everywhere else we're going to assign a 1. Now, well, actually guys, I messed up. We need to call that something. So I'm going to call that gen recode. So for gender recode. Now if I look at the correlation between exam and gen recode, I get a point-biserial correlation of negative 0.0047. And guys, I can do the same thing with core test. I can carry out a correlation. Now, something kind of cool about this is the correlation test. The p-value that you get is going to be the same as if I ran a t-test of exam over gen recode. So guys, notice that the p-value is the same thing for the correlation coefficient as it would be for the t-test. So kind of cool stuff. I don't know. I'm amused by that. Guys, let's dichotomize exam. Let's say I'd like to take a look at the relationship between a dichotomous that I create. See, before all I did was with gender is just assign to zeros and ones. But let's take exam and actually I don't know what the range is for exam. So the range goes from 2 to 100. So let's do standard measures. If it's above 60, they pass. Below 60, they fail. So I'm going to do another if else. Call it something. So if I have exam greater than or equal to 60, pass. Otherwise, we're going to fail. Now, to do a biserial correlation, we need to install polycore. And it'll take a while. All right, access the library. And the command for to run a biserial correlation, we put our continuous variable first. So in this case, we would look at maybe anxiety over exam recode. So guys will get a negative 0.448 as the polyserial or the biserial correlation between the exam that we dichotomously coded. Now, I will get on my little soapbox here and say that I think this is just a statistical nightmare to take something like exam and recode it. So you're really taking something that has natural variation, you know, a continuous measurement, exam score, and by dichotomous, you're significantly decreasing the variation. I think that's a statistical no-no, but you know, guys, it's done. And sometimes I guess research goals and research questions would lead you to perform something like that. So gang, I am done. Hopefully Alexa doesn't flip out on me here, but have a good one.